That's a good distance. What's up, guys? What's up? Can you all hear me in the back? Yeah? Awesome. Welcome to our first clustering meeting. This was going to be our first kind of informational night. This kind of meeting is going to happen 3 times now. This is the first one. Our second one will be in 2 weeks. And that's how it's going to go for the rest of the quarter, with our main project-based meeting next week. We're going to be having these meetings will be recorded. So if you guys can't make it in the future, then these intro meetings will be recorded. And our project meetings for our projects next, for the second meetings in the cluster, those will not be recorded. So just as a heads up, if you guys can or can't make it next week, that's how these will go in the future. But for now, welcome to our first informational clustering night, intro to clustering. Please provide us feedback at the end. We're going to be giving out a form. Your feedback will make us do better in the future. So with that said, let's get it rolling with first an update.
All right. The logo challenge is still open for anyone who's still considering on submitting that. As promised in the message on Discord, we're going to announce the prize now. We're going to be giving the winner somewhere between a $15, $20 Amazon gift card, and then we're also going to be offering them a spot to work with us and make some merch for later this year. None of us are really good at that, so what we're going to hope for is getting some stickers, getting some t-shirts or sweatshirts going for people who are really interested in getting that later. And realistically, this is going to be offered to the winner, but we're also going to be posting all of the cool things that we get in the Discord for people who are interested in seeing what came out. Again, competition is open until the 17th, so like midnight next Monday is when we'll stop accepting submissions, and then we'll have our final decision by the Monday after that. The link is already in Discord. I'll make another announcement as soon as the meeting's done with whatever you want to do there. There's a couple of guidelines as well. Yeah, best of luck, and hope to see your submissions soon.
Just to add on to that, I did get a couple questions, but last meeting about whether you can make it use a artificially generated logo. And I say, if you're gonna do that, go for it, but make sure you make some edits to make it actually say either Santa Cruz AI or SC AI, something like that, because when you do generate it, it doesn't actually include the right word. So if you want, you can go the artificial generation route, but make sure you edit it and make it look accurate to our club. All right, let's get into the meeting. So as mentioned by Rahul earlier, this is going to be the introduction to clustering meeting. So I'll be going over what is clustering, the different applications, how computers understand clustering, and a couple algorithms related to that. And so that'll be our introduction. And next week, we'll continue on with a deeper dive into clustering. So we'll go into a little bit more algorithms and have a workshop where we have a project where people can complete it and have some coding experience to put on your resumes or just practice on your own. So first off, what is clustering? Clustering is essentially just a method that is able to group data points based on similar properties. As we can see in the picture over here, we can see that all the data is unlabeled. Well, it is highlighted, that is part of the clustering process. And because it is taking in unlabeled data, that it means we are using unsupervised learning. So if you remembered, unsupervised learning essentially just means that the inputted data is not labeled. So if you had a picture of an apple, you wouldn't actually say that this is a picture of an apple. You just have a picture of an apple. And if you give the program a picture of a red circle, instead of saying, hey, I think this is a red apple, it'll just match that, hey, this looks similar to the red apple, or the picture that is the red apple. And so as we can see here, this diagram contains 2 properties, or also known as 2 dimensions. And so we'll be, for the most of the examples here, we'll be going on for 2 dimensions or 2 properties, but just know that it can very easily be a lot more than just 2 dimensions. For instance, later when we talk about irises, there's not only the iris petal width, length, but there can also be sepal length and width as well. So it's oftentimes a lot more than 2 dimensions, but just for showing off all of the examples and trying to understand it, we will use 2-dimensional examples only. So the main thing that I would like to get forward is clustering compared with classification. There is a lot of overlap, as clustering can be used as a classifier, but I would just like to put this out that classification, its main goal is to take in data and then classify it based on the data given. In this case, classification is typically used with supervised learning, meaning that it requires the data to be labeled beforehand. And then again, clustering doesn't have to be labeled, but can sometimes include labeled data when it is used in classification processes. So, why do we use clustering? Can anyone give me some applications for why we would use clustering? Yeah. Oh yeah, and if you have a large amount of data, clustering is a perfect solution for that, especially when it comes to images. For instance, if you have a lot of satellite information and you're trying to detect what a forest is, you can use similar features such as if you have color or even more like you have temperature data, you can group things by similar properties and be able to classify what's a forest, what's a grasslands or plains that way. Any other applications before I go on? All right, perfect. So one easy application is recommendation engines. In this case, we'll be looking over Netflix's. Obviously, Netflix will have a lot more of a complicated clustering algorithm than this, but this kind of just goes to show the application, where it can be used. So as we see here, we have a lot of movies and TV shows put on a graph based on how slow or fast it is, or serious and casual. So in the top of where everything's more serious, we have Black Mirror, Breaking Bad, Squid Game. And we have a little bit more casual, you know, Parks and Rec, The Office, and those fun things. And so based off of the categories, we could visually identify that there's probably around 4 major groups, at least in this diagram. We have the slower category, the serious category, casual, and faster. So these are all grouped up based on these similar properties, and therefore it can be considered a clustering algorithm. In this case, the reason why we would want to cluster them is, let's say you watched Parks and Rec. You finished watching and binging all of Parks and Rec in 2 days, and you want to watch the next one, or at least Netflix wants you to continue watching a show. So what show should they recommend? Well, obviously, they probably wouldn't want to recommend Grey's Anatomy after you watch Parks and Rec. So to choose it, they can find, okay, what are the shows that are similar in properties to Parks and Rec? And so that would be this green circle cluster over here. So they would most likely show you The Office or Community after watching Parks and Rec. Similar with if you watched The Adam Project. If you watch The Adam Project, you'll be more likely to watch Arcane than you would be Black Mirror. So as we saw in the last example, we just kind of eyeballed what should be a cluster. However, computers can't just eyeball what they believe to be a good cluster. So we have to come up with some sort of algorithm or some method to actually tell the computers how we should identify what a cluster is. So we can go over a couple of ways that we can be able to identify them with specific rules. So we'll go look at this, all these plots over here. So these are pre-labeled data points. We have obviously our blue cluster, our green cluster, and this red cluster. So if we look at our first point, this white dot over here, and we try to classify that as part of a specific cluster, I think we can all agree that it's probably going to be part of the blue cluster, just because it is surrounded by the blue dots. But how can we argue this? Can anyone give me an argument for why we actually believe it is blue in terms of a hard explanation? Yeah. So you hit a good point about what is surrounding exactly. So we'd have to be talking about this in a more explicit language. So rather than just saying, oh, these are things that are generally close to it, because computers don't know what close means. It only knows what specific numbers are. And so, for example, when you said surrounding, you could say, okay, when you look in 360 degrees, what are the dots that it finds? So when we go look at it, all 360 degrees, it's surrounded by blue. So if you want to say it's surrounding, we would say something like that. So that'd be one great way of classifying this as being a part of the blue cluster, because everything in all 360 degrees, or at least 350 if you include this gap over here, to be part of the blue cluster. Yes? Yeah, that's also another way. So if we look at over here and say, hey, this dot is anything within 10 units of distance is going to be part of this cluster, we can then see, oh, only these 4 are within a 10 distance away, and then identify it as blue. That's another perfect way. So now we can go look at our next example. So instead of the dot being in the blue cluster, we put it over here in the red cluster. So we can use the example that he suggested where we look at what are the close within a certain proximity, but our surrounding algorithm no longer works because when we only look at here, we say, hey, only about 60 degrees or 120 degrees is actually surrounded by red, whereas there's a lot of blue and green. So it's not a perfect solution. So does anyone have any other ideas for how we can classify this as red? Because I'm assuming we can identify this as being part of the red cluster. Yes. Yeah, that's a great way of identifying it. So we see here that we take the average distance of every single one of these dots, or at least the red ones. We say, oh, that's an average of 20 units away. And we find the average distance between each of these dots and the white dot and say, oh, that's 50, green is 40. Therefore, we believe it is red because 20 is less than 30 and 40. I forgot what numbers I used. That's a great example. So what about this last one? This last one, it's kind of hard to say. Is this blue or is this green? Because as you can see, the nearest dot is technically a blue cluster, is part of the blue cluster. So with one example, we could claim that, hey, this white dot should be classified as the blue cluster. I guess we'll ask this one final time. Does anyone have another algorithm that we can use to identify what this white dot is supposed to be toward? Is that a raised hand? I can't tell. Say again? All right, yeah, so we say, oh, if we look within 10 units away, so it'd be these 20 or something, or not 20, I don't know where I came up with that number. These like 5 dots. We could say we can find the distance between them and then average only the distance, only the dots within that certain distance, and be able to get, hey, the average distance of the nearby green ones is 5 units away, whereas the average distance of these 3 blue ones are 4, and therefore we think it's green. That's another great example as to how we can cluster. Another way is, like I talked about, we can look at the nearest data point, in which case it'd be the blue, and so we can identify as blue. But what if we also looked at the nearest 3 data points? So if we looked at the nearest 3 data points, we say, hey, there's 1 blue and 2 greens, and therefore identify it as a green. That is a great way, and it's actually called the K nearest neighbors algorithm, which we'll get into now. The K nearest neighbors algorithm is technically a classification algorithm, but we'll use it just to teach how computers think about clustering as a whole. So it being a classification algorithm, it means we are using supervised learning or the data is labeled. So as we saw in the previous slide, all the data was labeled as blue, green, or red. So as we see, so we have our training data, which is the data that is labeled. So all the blue, the red, and the green data. And we have our test data. In this case, that's going to be represented by our white dots. This is the data that we want to be able to classify as either blue, red, or green. And technically, we do know what this actually is. But for testing purposes, we're going to pretend that we don't. We're going to predict what it is and then check to see if we got it correct. And based on that, we can get an accuracy score. So when we see K nearest neighbors, what does the K mean in this? The K is a hyperparameter. So as we mentioned before, a hyperparameter is a pre-decided parameter that we can put into our algorithm to help change the result of our model. So in this case, K is the number of nearest neighbors, also known as the nearest data point. So for example, if we look at when K is equal to 1, we look at what is the single nearest data point to our white dot. In this case, it's going to be the blue. So when we say, all right, when we have K equals to 1, by using the K nearest neighbors algorithm, we can then predict that this white dot is going to be blue because its nearest neighbor is blue. So now what happens if we say, what if K is equal to 3? Well, then instead of just looking at the nearest one, we look at the 3 nearest neighbors. So this blue, that red, and then a second blue. So then we can go and look at all of them and say, hey, there are 2 blues and 1 red. Therefore, we're going to classify our dot as being part of the blue cluster. We can expand this out into K to be equal to 6. So when K is equal to 6, we're going to classify our dot as being red because there are 3 reds, 2 blues, and 1 green. So we can go into a little bit more of a description. Oh, I forgot I had animations. Anyway, so this is a more descriptive way. So when we're actually trying to program this, which we'll see later on, this is kind of the thought process or the process at which we would go through this. So first we have our data, make sure that all of our data is pre-classified. So all the training data, we have a yellow, we have a green, we have a red. We have to first find the distance between every single one of our data points and our testing data. So we'd say, oh, look at this. Our yellow is 2.1, our other yellow is 2.4, 3.3, 4.5, and so forth. Then, now that we have all of our distance aggregated, we can put it into a list or an array, or whatever you want to call it, depending on what language you're using. We can then sort it out and then cut off anything that is not within k nearest to the dot. So in this case, we're going to be using a k value of 4. So we have our 4 closest dots. We have the yellow, which is 2.1, another yellow, 2.4, green 3.1, and a red 4.5. These are our 4 nearest neighbors, and therefore we can compile them together. So when we compile it together, we get our 3 classes, which are going to be the yellow is 1 class, the green is a second, and the red is a 3rd class. And we have an occurrence or number of occurrences for each of these. So as we can see, the highest number of occurrences is part of the yellow class, and therefore we classify the point as being yellow. So I talked about earlier that there's some value of k. Well, what do we do with this value of k? Technically, there is no perfect way of identifying what the best k value is. So typically, when you have your training data, you have to do some trial and error to figure out what seems to be the best value of k. Sometimes you want a value of k that's like 10, but sometimes you have a lot bigger data where you would need a value of 100. One example of why you would need a bigger value of k is that you want to get rid of outliers. You want to get rid of outliers. So if you have a k value of 1 and you have a weird outlier, like we saw in this one, we have 1 outlier, then that's probably a bad reason to have a low value. So if we have too many, then we get an issue where we take all of these values, and therefore because there's more blue, there's more blues than greens, we classify as blue. So you want to find a sweet number in the middle. And so we can find the sweet spot by trial and error. There are a little bit more optimized methods, but trial and error is our best method that we can do currently. So for now, we want to take all of the data that we do know and split it into testing and training. This is something that you'll see very, very often throughout almost every single machine learning model that we'll introduce or you'll find out on your own. So typically, we'll break it into an 80 to 20% split. So that means 80% of data is going to be your training data, 20% is going to be your testing data. These numbers are very arbitrary. Some other percentages also work, such as 70-30, 75-25. But for the most part, we can do something around 80-20. That means 80% of our total data is training, 20% is testing. In this case, our training data, like I said, is going to be the ones where we do know the color or the cluster that it belongs to. So the training data is our red stars and the green triangles. And our testing data are the ones that we don't know. So we were able to see how good a k value is by just testing it on all of our testing data. So we can say that, okay, let's try it with a k value of 3. And let's say because our k value is 3, we classify this unknown as a green triangle. Let's say that is actually an incorrect guess. So that means currently, of its 1 sample, we have an accuracy of 0%. And so we would do this with every single one of our testing points and eventually get an accuracy of, let's say, 70% accuracy, also known as a 30% loss. And we would be able to test that for a bunch of different values of k. Eventually, we come up with and say, hey, after testing all k values between 0 and 90 or whatever, I noticed that the value of 45 gave us the lowest error. And so when we go to run our algorithm on true data, so data that we don't actually know, data that we'd find in the field, that would be our best guesses. Another thing that we can change to help boost our algorithm is what distance function that we are using. Earlier, I heard something about using a square root function, which is a good instance of Euclidean distance. These distance algorithms, you don't need to memorize. Don't let them make you scared. Euclidean distance is essentially just Pythagorean theorem, just with multiple dimensions. So as you see here, it's the square root of the difference of something squared. And normally it would be a minus b squared, and then c minus b squared, and then the whole thing square rooted. So that's the simple Euclidean distance. For most cases, Euclidean distance is what we're going to be using. However, there are a lot of other distance metrics. There are infinite number to be particular, because you could just make up your own. You could say, oh, our distance is going to be x minus b plus 90. It could be whatever you want. And as we see here, we have the Manhattan distance, which is similar to Euclidean distance, but without the having to square and then square root later, we just take the absolute value and sum of that. Additionally, there's Hamming distance. This one's pretty straightforward. If x and y are the same, the distance is 0. If they're not, it's 1. Not as useful. Sometimes it has its use cases, but in this situation, probably won't be as helpful. Yes, question. Oh, so because it's a summation, let's say there are 5 dimensions. We would say, okay, x, the 0th dimension of x minus the 0th dimension of y, take the absolute value, and then the sum over that. Oh, yeah, sorry. So the I is kind of the index of each of these coordinates. So think of them as an array. So your x, let's say the x is 1, 2, 3. The 0 dimension of that would be 1. The first dimension would be 2, and the third dimension would be the 3. But yeah, you can make up your own distance algorithm. There's tons of them. If any of you guys have done things with polar algorithms, you can think of the difference in terms of the angle rather than the actual physical distance in a linear scale. So tons of different distance algorithms. Don't worry if this seems complicated. It's just another thing that you can change. So now we can get on with actually playing with k-nearest neighbors. So you can type in that tiny URL, or you can find our slides, which has the link on our Discord, and we can go bring it up the k-nearest neighbors Colab. So I'm assuming most of the people have used Colab in at least one of their classes, and we'll go over how it works, how it's coded up. And at the end, everyone can play with it, make their own distance function, and just optimize for the value of k. And we'll see who can get the highest accuracy score. I will keep this up for another minute until I will switch over to the actual Colab slide. Again, if you don't want to type this out, you can find it on our Discord. And if you didn't bring a computer, that's okay. Just share with your neighbor. I see most of you have brought your computers, so good on you. Also, from now on, we will be having these small Colab notebooks, so everyone bring your computers from now on if you did forget today, but it's okay. Raise your hand if you still need the link. Perfect. Okay, I will move on to the Colab. What? One question? 1%. What? I don't. Oh, okay. We're good. I forgot to open this earlier. Hopefully this works. All right, perfect. So everyone can see this on their screens, right? All right, good. So if you want, you can run this, but again, this looks to be pre-run, so I'll just be using the current output. So currently we are going to be coding the KNN algorithm. It is already pre-coded, but we'll go through it together and we can change stuff at the very end. So first, we're going to be using the sklearn dataset. So it contains a lot of different data sets. In this case, we're using the iris data that I mentioned earlier. So we have 4 main different types of data. So that means it's going to be a 4-dimensional KNN problem. So we have our sepal length, sepal width, petal length, and petal width. For those who don't know what a sepal is, or if I'm completely mispronouncing it, it is essentially the green leaf that's right underneath the flower. Don't have any pictures of it, but if you want to know, you all have computers, you can check out what a sepal is. And I'm assuming everyone knows what a petal is. So as we can see, we have the data split up into 4 different types. So we have our feature names. As you can see, these are all the feature names that I just mentioned. So sepal length and so on. Then we have all of our data. So this is all the actual numbers that we're going to be clustering based off of. So the first number is going to represent the sepal length, second number is sepal width, petal length, petal width, and so on. So we have all this data that we have imported from the sklearn dataset. Then we have our target names. So these are going to be the different classes of irises. So there's going to be the setosa, the versicolor, and the virginica. Those are going to be our 3 classes that we're going to try to predict. And finally, we have the actual true data. So this is the actual types of every single one of these flowers above. So if we notice, there's a bunch of them. There's a bunch of 0s, 1s, and 2s. These 0s, 1s, and 2s just represent the index of our actual type. So instead of writing setosa, instead of all the 0s, we just represent it as a 0. All the 1s represent versicolor, and all the 2s represent virginica. And this lines up with all of this list of data. So the very first like 10 or so of these are all going to be the 0, which I think is Setosa. So the first like 10 or so are Setosas. What looks to be the next 15 are all versicolors, and the last another 10 are virginicas. And that's how we label all of our data. So again, this is labeled supervised learning. This is also a classifier. So here we have this image for everyone to view just in case they forgot the actual algorithm. And we have our first start of code. So in this, when we code, we typically are going to be using helper functions. So if you're just brand new, helper functions essentially just methods or functions that we can create that are going to be used later on in our algorithm. So these are just things that we're going to have to reference pretty often. So we're just going to code them ahead of time so our code doesn't end up looking like a huge bundled mess. So we start off just by coding Euclidean distance. This is very simple, just going through a for loop of the number of dimensions that are within our data. So P1 is going to be the data, so that would be the steeple length, width, petal length, and width. So we go through for loop of all that, and we find the sum of the difference. I don't think I need to explain how Euclidean distance works. Everyone should understand. If you have any questions, don't be afraid to ask, but you can also relook at the slides and everything like that. Then we have our voting function. This voting function is the same thing as we have as this third step. So taking in a list of all of these points, we can then find the total number of occurrences and take out whichever one has the most occurrences. In this case, yellow. But here we'll be taking in all the zeros, the ones, and the twos, and spitting out whichever one is most common. So you can go into this individually, or you can just trust that the code works. But we'll go on to the actual setting up the data now. So now we have our functions, our helper functions all coded up. We can start off by splitting the data. So on our first step, we take all the data. So now that we have our data imported from the very first cell block, we can split it up into our training and our testing data, as mentioned earlier for optimizing for K. We'll take in our known iris data and our unknown iris data. Technically, they're all known, but we have to split up into training and testing data. So the unknown iris will be our test data, and our known irises will be our training data, so the ones that are labeled. So we have the data set, which will include the ones, all the numbers, so the 1, 2, 3, 5.4, those ones. And the types are going to be the whether it's a 0, 1, or a 2. So we're going to set our value of K, and we're also only going to be looking at a single iris data, or a single data for a single iris, sorry, instead of doing them all at once, just so that we can see how everything works. So on our 0th iris, or the first one, we can see that it has a sepal length of 5.8, width of 2.8, length of 5.1, and so on, and is also a virginica. This works well, as we can then find the distance between this iris and every single training iris data that we have. So we start off with a for loop and loop through every single one. And now we can see our distance metric. So distance metric is essentially the Euclidean distance, as we said above. And we were able to find all of our distances, compile them. So now that we have a list that contains both the distance and the iris type, and put them into our completed distance list. So as we can see here, this is our completed distance list. So you have all of our iris number 1 has a distance of 0.5 and is a virginica, and so on. You can look at all these individually on your own, and we get all 120 and all their distances. Next, this is where the meat of everything is. So this is where the KNN truly shines, where we actually find what are the K nearest neighbors. As we saw earlier, we set K to be equal to 10. So we're going to be looking at the 10 nearest neighbors. And we're going to start off by sorting all the distances. So this line right here uses lambda, but essentially all it does is it sorts all of our compiled distances by how far away they are to our single data for the iris. We can then cut off or slice the data such that we remove all the data that is farther than the 10th index. So this is from 0 to technically 9, because we start off with 0. And then once we have that, we can just make some more small changes. So just data manipulation, so that when we put into the vote helper function, all it contains are 0s, 1s, and 2s instead of the actual distances, because as you know, we no longer care about the distance once we've cut off the rest of the data set. So once we have our 10 nearest state irises, we could see all the distances and the types. So as we see here, these are the nearest ones. So from 0.1 to 0.3 units of distance away. And we can see a pattern. There's a lot of virginicas with one versicolor. So based on that, we could probably guess that our iris is going to be of the virginica type because the 10 nearest irises, or 9 of the 10 nearest irises, are considered virginica irises. So we would guess that the answer is virginica. And that's it. That's all KNN really is. It's those 2 helper functions mixed with these 3 relatively small cell blocks. Essentially just grabbing the data, looping to find all the distances, and then cutting off the distances and then calculating which one occurs the most. So I guess any questions here? Okay, so can I just get a thumbs up to see if I'm explaining this well for anyone who's lost? Just make sure. All right, that looks pretty good. I see a lot of thumbs up. Perfect. All right, so now putting it all together. So essentially, I'm just copy pasted all the stuff I had from the previous examples into just a single function. So as we here, we have guess iris type. So this takes in all the known irises and then a single unknown iris and just does everything that we did before. So this is perfect for classifying a single iris. However, we often want to predict more than one iris. We want to predict entire set. So the entire testing data set we want to predict and find the accuracy of how good our KNN algorithm is. So I create another function called KNN run. This, all it does is it loops through all the unknown irises, runs it through the guess iris type, and that will guess what iris type it is, and check to see, is the predicted iris type equal to its actual iris type? Because we do actually know the iris types or classes of the testing data. If it is correct, good. If it's not, then we increment the number of incorrect guesses. Because at the very end, we can then find the percent error, which is just the number of incorrect guesses by the total number of guesses. Pretty simple stuff there. And just like that, we have our KNN fully completed. All we have to do is run KNN run on our known iris data sets and our unknown iris data set, including our K and distance metrics. This is where you guys can do your own coding. So as we hear, I have coded in the Manhattan and Hamming distance as shown in the slides. And I've also left a blank area for everyone to code in their own distance function. So I'll give everyone about 5 minutes. You can discuss with your neighbors or just go straight into coding about creating your own distance function. And feel free to run all the code that we've done so far and just see how everything works. If you want, tweak what's already been. This is for everyone to play and mess around with. Yeah.
Just one second.
Yeah, okay. Oh, well. That's fine. Also, at the very end, I will ask to hear what some people have chosen for the distance functions, just because I'm curious. So keep going, guys. Anger. Yeah. I cannot hear you. Yeah, so if you can't find the slides, they will be in Discord under the recording section. The recording section has all of the resources that we have created, so that includes both slides and the actual recording. That's the recording and all of it. I was gonna add everyone with All right, about how much time do we need? Are we all done, or should I give another couple minutes? Couple minutes? All right, yeah, I'll check in a bit. What? And this is just fine. That's the control. Do you like my test? I have it go through 100 different states. All right, don't look at that. Also, I forgot to put the master slides, the master, I didn't have the master Python. I guess it was just good. All right, so just due to time and everything, I will pause you guys there. If you're still coding, continue coding, but I'll try to take some volunteers. Who wants to kind of say what their distance algorithm that they made up? I'm just curious to see what everyone's come up with. We'll start here.
I made one where instead of having all like different dimensional distances together, it just takes the largest dimensional distance and uses that.
That's a very creative way. Again, that might even outperform Euclidean distance. I don't know. You really don't know until you try it. Some data miraculously, you can use like a random number generator and that might work better just due to randomness. Any other ones? Yes. That works. I guess one thing you might be worried about is some negative numbers coming into play, but hey, it works. It's a distance function. I guess I'll take one more. Does anyone have another distance function? Yeah. Okay, yeah, that also works very well. That is a nice implementation on the Hamming distance. Again, there are a lot of distance algorithms which are just slight modifications to an existing distance algorithm. That way, some are like optimized for one process, other ones are optimized for other ones. And as we'll see in the next meeting, we can see how we optimize off of a certain algorithm that I guess I'll go into a bit. All right, so next we'll actually start running KNN. I'm assuming a lot of you have already skipped ahead, but for those that haven't, here's where we can actually run KNN from scratch, where everyone can play with a K value of their choice and a distance metric that they have chosen. So I'll give everyone about another 5 minutes to play around with different K values, messing around with different distance metrics, and we'll see which K value with what distance metric actually gets us the best error or the lowest error percentage. So everyone go through that, and in a couple minutes, I will ask what everyone's results are. And the winner is whoever has the lowest percent error. Simple as that. Let's know the answers. Who's the 4 data? Oh, so I think what I did is I put up to the top and squeezing the lid. So I was trying to lose water. Isn't slipping hazard here?
It's over.
So what is the minimum? What is that? That's probably like 13.
It's like. Yeah, that's like 15.
It doesn't go to 13. That's fine.
Yeah. It's too big to
This guy just really wasn't paying attention. It was like, oh yeah, the lowest value is 13.5.
Completely.
Technically, you could say 13.5 is a random chance, but
Yeah.
13 on first.
But the flame. It's like it's very. I mean, ran once on one time. Random state is random. Talking about the challenge, the guy is not.
I'll be sending more stuff about that in the channel.
Okay, cool. I just wanted to check that out to be transferred in class.
Yeah, no worries. I'm
Um,
everybody outside.
But I wanted to make sure that there wasn't any.
Yeah, you're all good. Take care, man. See you next week.
You should also give it out. I'll get a rating of where that was set to. Go over all the things that were in that you can do. Essentially, this was
What's your random state? What's your random state?
It's 0 to 1,000. 0 to 1,000 changed it?
No idea. Yours.
Sorry, what? Oh yeah, the seed. You chose the seed to be. Okay, well, I chose the seed apparently. So I set the seed to be anything between 0 and 1,000, or everything between 0 and 1,000. So it runs.
For random state. This is 1,000 times.
It was like 1,000, yeah, and then it does that 40 times.
So okay, that's each seed 1,000 times random. So gross.
Not
No,
random.
no. I mean, like the random between seed.
No.
Random state in range. Oh, so it does a random state 1,000. Like just 1,000 random states.
Yeah.
And then average.
Yeah, random state 0, 1, 2, 3, 4, 5, 6, 7, 8,
You
9.
run this 40 times.
Yeah.
With a larger data set. But it works.
It's just for testing purposes.
No, I know. It's just.
I don't know. I would say that this was fact for the code and actually testing one. All right, how is everyone doing? Is everyone done with testing? Yes, raise your hand if you need more time. All right, a little bit more time. All right, I'll give everyone like 1 more minute and then we'll come back together. Okay, everyone, we're gonna come back together now. So I'm gonna assume everyone had enough time to play around with different K values and different distance metrics. Did anyone find that their distance metric worked out better than Euclidean distance? I see one. Did yours work out better? What was your distance metric again? No, what was your distance metric? Sorry. Okay, I'm gonna pretend like I know why that works, but apparently that works out better for this data set, right? So again, some distance metrics just work better. All right, so just get a raise of hands. So I'm assuming we found good K values between 10 and 15. Yeah, does anyone get a good K value that was outside of 10 and 15? No? Okay. Raise your hand if you think you found like the best K value, I guess. Yo, the person over there. 15? 15? So did anyone, or what was your percent error? I'm curious. 2.9% with a K value of 15. Did you use the Euclidean distance? Euclidean distance? Did anyone beat 2.99% error? No? All right, that's good. All right, we're gonna go back to the slides. So that was a little taste of what we do for coding. Next week we will do a little bit more in depth where everyone can code a little bit more of the algorithm. All right, guys, we're gonna talk about k-means clustering. Can I get everyone's attention, please? Can I get everyone's attention, please? Thank you. All right, so we're gonna be talking about k-means clustering. So this is a very, very common clustering algorithm. It is very common to use because it is very easy to run. Again, as we see, is pretty much just 3 steps, and it is very small and like compute light to process. So other algorithms we'll talk about later require a lot of GPUs. This one can very easily be done on a very small GPU, even your CPU, for instance. So this one, as you can see, it also has a K value in it. So again, a hyperparameter that we have to choose for our algorithm. In this case, K represents, instead of the nearest neighbors, it represents the number of clusters that we are trying to guess. So in many cases, there are going to be a certain number of clusters. So as we see in the GIF we see over here, that the number of clusters is going to be 3. So we're just eyeballing it here. We're guessing that there's going to be 3 clusters. Us being able to guess how many clusters is both good and bad, as if we can very easily view the data, as we see that this is 2-dimensional, therefore easy to view, we can identify how many clusters is going to be. However, when we have 10 dimensions and millions of data points, it's going to be a bit harder to determine the number of clusters that we think are going to exist. So that is a bit of a downfall, and we'll have to try to, again, test to see what values of K work the best. So that's a bit more of a challenge to figure out the optimal value of K here. So we start off with the algorithm. The first step is to create centroids. A centroid is essentially just where we predict that a cluster center is going to be. So as we can see here in our GIF, all the X's are going to be our centroids. So the first step is to randomly place a centroid on a specific data point. So this is where we start off with randomness. Because there's randomness, we will also want to be running this algorithm multiple times and taking the average, as if we get one bad at randomness level, then we'd get an outlier, and we don't want outliers, so we run this multiple times. Anyways, the second step is to then match and classify every single data point to its nearest centroid. So that means, as we can see in our GIF, that we have all the green data points, and all those green data points mean that that data point is closest to the green centroid rather than being close to the purple or the red. And same thing with purple and the red. The purple data points are all closest to the purple centroid rather than the red or green. We can then relocate or move each of the centroids based off of the mean position of all of its matching data points. So let's say all the data points are to the bottom left of the centroid. We would then move the centroid to the bottom left to be the very center of all of the data points that are matching in classification. So we will then keep repeating all these steps. As we see, the centroids will keep moving until it slowly stops. And once it stops or stops moving, or we say, oh, run through it at 50 epochs and then stop, then it will stop. And that will be our answer to what is considered a cluster and how the algorithm decides. So we can go over this step by step with a slowed down version of this GIF. So we start off by selecting where our centroids are going to be. This is a random process. So as we can see, we have our green centroid in the top middle. Our purple centroid gets placed in the middle right. And then the red one gets placed kind of out on the edge in the bottom corner. We can then classify all of our data points. So we set all of the data points to be to their nearest centroid. So notice how all the green data points are close to the green centroid. All the purple data points are close to the purple centroid, and same with the red one. And so this is our first step, making sure that we have our centroids and classifying every single data point to its matching centroid. Our next step is to then move the centroids. So notice how the centroids move. So the green one, it moves diagonally down to the left because that is the center or the main location of all of those green data points. That gets moved. And then also the purple one gets moved. So notice how the purple one's going to move down to the right just because that is also the center of its mean data points. And the red one will move a little bit up into the red as well. So another thing you'll notice if you are able to catch it is that we also have to reclassify all of the data points as well to their new nearest centroid. So this one's right here. This is purple now, but it used to be green. It used to be green because the centroid for that was green used to be here. But now that it's over here, this data point is actually closer to this purple centroid than it is to the green centroid. And so these here also get changed a bit, as we can see. We swap between the two. It goes from purple to red, purple to red. And we can continue this until we have our final data. And this will work. And we were able to eventually classify all of our data or cluster all of our data to that specific cluster based on this very simple algorithm. We will go over this algorithm again in next week's lecture, as it is the main coding algorithm that we will do together, or individually technically. So any questions about this one? Yes. So you have a point. So not always will this clustering algorithm be correct. Oftentimes you'll notice that, especially with lots of clusters, you'll have a situation where two centroids are actually right next to each other or on the same cluster. So as we see in the beginning of this this GIF, the purple and red are really close to each other. That can and will happen very often within our algorithm. So the algorithm itself is not perfect, and we'll go later into see how we can improve on this in the going further lecture, or not lecture, slides presentation. Next week, we'll go into a little bit deeper dive as to how we can fix it. So again, it won't always be perfect, but yeah. That is all for the presentation. Thank you everyone for coming. Next slide. Oh, wait, we have everyone fill out this QR code just for some questions for next meeting and have everything get set up. Also, we will be having a meeting on Thursday. So that is 3 days from now, 4 days. I don't know the days of the week, but that will be a speaker event. So we'll get Professor Leilani Gilpin to come in, kind of talk about her experiences as both in academia and in the corporate world as part of being an AI researcher. So I hope everyone can come on Thursday. We will post everything in Discord announcements. Location will be here at the same time, Thursday. Thank you.